In this video, I'd like to spend a little bit of time taking a look at measurement system analysis, sometimes called MSA, along with a particular type of experimental study called Gage R&R studies. Specifically, we'll introduce you to some of the concepts related to MSA, including accuracy and precision, and then we'll walk through some of the rules of thumbs associated with a Gage R&R study. I'll probably spend a separate video on taking a look at actually walking you through a Gage R&R study using QI macros as the tool of choice. Frequently, at the beginning of any process improvement project, when you're going out and collecting current state data, or when you're going out and collecting future state data, you want to be able to answer the question, how well are you able at collecting data on the same phenomena that happens over and over again? Do you get the same results? Do you get the same recorded results? That's really the topic of something called measurement system analysis. Now, we've looked at earlier cases in which we've done what I would call a level 0 measurement system analysis. That's where we're just checking to see if the data that's being collected is in any way a reflection of current state or values that couldn't happen in the universe that we live in. For example, we looked at time-based data in a pizza case in which the time that it got to the delivery driver was 17 minutes, but the time that it arrived at the doorstep for the customer was recorded as 11 minutes. Clearly can't happen in this universe, was a mistake in data entry value. I'd call that a level 0 measurement system analysis, just checking for obvious mistakes. We also looked at case data in which data that was being collected, we identified data elements that were missing, where either process workers or customers, either concerned about punishment or due to gaming conditions, had not actually recorded phenomena that had really happened in current or future state. In both of those situations, I'd call that a level 0 measurement system analysis. We do it all the time in both production, manufacturing, as well as service environments. But let's take it a step further. Let's say that you are capturing the relevant data, no missing data points are being ignored or removed. How well are you able at taking a specific phenomena and measuring it over and over again and recording the same values over and over again? Is the amount of variation that you see in your data set, is the curve or the fatness of the curve in the data that you're collecting a result of operational issues, machine issues, standard operating procedure issues, or is a large amount of the fatness of the curve a result of the inability for you to measure consistently over and over again the same phenomena? That's what measurement system analysis is all about. Now let's take a look at a couple of terms that are key to any sort of measurement system analysis. So within any sort of measurement system analysis, a couple of concepts that are real important include accuracy and precision. And I like to use a bullseye on a target to help with the understanding of the two. Accuracy is about if this bullseye were the standard or the part or the phenomena that we knew happened, and it had a true or real value. If we were to measure that phenomena or that part or that transaction, the same one over and over again, what would its average be over the course of multiple measurements? We call that accuracy. In this particular picture, the average of all of those data points is exactly what the true value, the true standard is. We'd call it accurate. But the reality is that each one of those recorded values, very few of them actually are hitting on the true standard. So, well, technically it's accurate because the overall average of these data points is right on our standard. It's not very precise. It's all over the board. In the next example, we're taking a little look at precision. So if the bullseye is the true value of the phenomena that we're trying to observe and record, we were unable to capture the true value, but we were very consistent in the output recordings that we put down. It's precise, but not very accurate. So the goal of a measurement system analysis is to try to make sure that when we are observing and recording phenomena that's happening in our process, that we're both accurate and precise. If we have a good measurement system, we'll have both of those things. Accuracy includes elements related to stability, or over time, are we able to record the same phenomena the same? It relates to linearity, or throughout the measurement range, are we able to record the same value over and over again? Is the resolution appropriate for the type of phenomena that we're measuring? And what's the level of biasness? Is it offset or off-center in terms of biasness? Those are elements that help us to determine if we're accurate. For precision, it's about repeatability and reproducibility. And we'll take a look at repeatability and reproducibility next. So in many measurement system analysis studies or experiments, we're trying to determine, can we measure the same phenomena over and over again consistently? Frequently, when we run into problems, it's due to equipment variation or appraiser variation. Equipment variation we often call repeatability. Appraiser variation we often call reproducibility. To help me remember what's the difference between repeatability and reproducibility, I use this simple little phrase. Humans reproduce, equipment repeats. Humans reproduce, equipment repeats. Equipment variation or repeatability technically is the variation in measurements obtained with one measurement instrument used several times by one appraiser while measuring the identical characteristic on the same part. Whereas reproducibility is the variation in the average of the measurements made by different appraisers using the same measuring instrument when measuring identical characteristics on the same part. And the two concepts together are used to help calculate what we sometimes call Gage R and R, a percentage of how much of the total variation that we see in the system is related to the measurement system, and how much of the variation is actually related to the process itself, the set of activities, operator characteristics, machine characteristics that create output in a range of values. What we want to do in a Gage R&R study is limit the amount of variation that's due to the measurement system itself. In a formal Gage R&R study, what we'll do is we'll typically have multiple measurers measuring multiple parts, measuring those parts multiple times in a randomized order. And then we'll create an experiment in which we randomize the measurers and the parts that they'll be measuring, and we'll do it multiple times. The result is a formal Gage R&R study. Technically, it's a form of a design of experiments. The output from a Gage R&R study is what we're really looking for. We want to know how much of the total variation that we see is related to the process itself, and how much of the variation is due to problems with the way that we do our measuring. And the general rule of thumb is, if your Gage R&R study shows that you have 10% or less, you've got a robust measurement system, and you can then move forward collecting your current state and future state process data. If your Gage R&R study, though, shows that you've got over 30% of the variation due to the measurement system itself, you need to stop the process improvement project and step back and improve the way that you do your measuring before you go on and use this data for analysis of improving the existing process. First, we need to fix the measurement system. Then, once the measurement system is in a more robust, stable state, we can then be confident that the data that we're collecting is a true reflection of what this process is performing like. So, over 30% Gage R&R means stop the process improvement project, fix your measurement system. Under 10%, your measurement system is good and you can plow forward with the process improvement project. And if it's in this gray area in between 10 and 30%, that's where you'll need to make a determination. Do you have the time and resources available to make some tweaks to the measurement system to improve it? I call it the gray area. In the end, if it is in that gray area, you'll want to use your business savvy to determine whether or not it makes sense to improve the measurement system or keep it and move forward with improving the process itself. Running a formalized Gage R&R study is actually a pretty straightforward exercise. It requires a lot of data collection. It can be a little time sensitive, and there may be costs associated with it, especially if part of the measuring means that you have to destroy the particular part, destructive measurement. Within QI macros, the Gage R&R templates are already created for you and highlighted in yellow where you enter your measurement data and it does the calculations for you. Gage R&R templates aren't from QI macros directly. They're actually from a professional association, the AIAG, the Automotive Interest Action Group, and are accessible on the web. In addition to accessing them directly through QI macros. We've got the formalized one located right here that I'll walk you through in a separate video, how to read and interpret the results. It's not the only way to run a Gage R&R study. There is also simplified methods for doing a Gage R&R study. This will be the approach that we use in some of the casework that we work on in our catapult case, but a much simpler way. In the end, though, whether you decide to use the formalized method or the simplified method, you're trying to determine is the percent total variation that we're recording, is there over 30% related to the measurement system? If it's 30% or more, we need to stop and clean up our measurement system. If it's less than 10%, we're good to go, and we can then use this data for analysis of current state and analysis of future state. Gage R&R studies. Let's now take a look at running the templates in QI macros and interpreting the results.